All right, so I have to be honest with you. Writing ionic formulas might be the most important skill of all first semester. It just never goes away. We're going to be using ionic compounds till June, and we have to be masters of writing formulas. I mean, eventually I want to get to a point where I can take two compounds and chemically react them together. I need to understand their formulas in order to predict what products might form. So it's kind of a big deal. Now we'll try to make this as manageable as possible, and that there are some shortcuts that can maybe easily and quickly get us to the right formula, but I want to make sure that we really understand what's happening in an ionic formula. So they give me an example here of calcium sulfide. Let's look at that one first. So here's calcium sulfide. They're going to start by giving me the name. So I'll see something in the lab. Hey, calcium sulfide reacts with iron 3 oxide. They might give you the written out name, and I need to be able to find the formula so I can predict what kind of a chemical reaction will occur and eventually predict what products might happen. So first thing we got to do is be a freak about charge. We have to be able to find the charge on any element. And so when I see calcium sulfide, I go to my periodic table and I've got all the charges marked in. And so I know calcium is in the group that's +2. +2 for life. Sulfide is sulfur. That's in the group that's -2. Forever and ever. Sulfur and calcium. +2 and a -2. Awesome. So that wasn't hard, right? So now I go back to my little formulas, and I'm going to start by writing the charge. The calcium +2 or 2+, and the sulfur -2 or 2-, same thing. Then, let me get something straight. Here's what's happening in this compound. Calcium has a charge of +2. It means that we have 2 extra valence electrons to get rid of, right? Sulfur has a charge of -2. Sulfur has 6 valence electrons and would like to gain 2. Are you thinking what I'm thinking? Perfect, right? The calcium will donate 2, the sulfur will take 2. Perfect! These 2 atoms can bond in a 1-to-1 ratio. 1 calcium will give 2 electrons, 1 sulfur will take 2 electrons. They bond with a 1-to-1 ratio. And then that's how we write the formula. We would just write the formula as CaS. Done. And look at this. Ionic formulas are supposed to be neutral, right? Well, yeah, it's neutral right away. +2 -2, it's neutral. That's another way to indicate that it's a 1-to-1 ratio. If you look at the charges, and right away you have a +1 -1, +2 -2. If the charges initially just add up to 0, that's another indicator that this will be a 1-to-1 ratio in the formula. Or I can take a deeper dive and really study it by the electron transfer. 2 electrons donated, 2 electrons accepted. Perfect. 1 atom of each will make sure that all the electrons are transferred and both atoms have a full outer octet, right? Well, here's this other shortcut. So see what you think. The shortcut is called this crisscross rule, or the crisscross method. In the crisscross method, you do just that. Just kind of what they're showing right here. You still have to find the charges. There's no way to write an ionic formula without knowing the charges. And so I always kind of write the charges on top of the element symbol, the +2 or the -2. Then you just crisscross the numbers. So like in a formula, we never see like the little minus or plus as a subscript. So you can just crisscross the 2's. And then in an ionic formula, we always write our final answer as the simplest repeating pattern in the crystal. And so if I were to crisscross a 2 and a 2 like this, well, we would never write it as Ca2S2. That's just not necessary. By really thinking about the bonding, I know that it's a 1-to-1 ratio. And so then we would reduce that to just CAS. So in an ionic formula, the little subscripts should always be the simplest whole number ratio. And that's how we would report the formula of the crystal, the simplest repeating pattern in the crystal. So if you crisscross the numbers, the 2 and the 2, and then you say, oh yeah, I could simplify that, then do it. Simplify it as much as possible. If you wrote Ca2S2, that would not be correct. That's just not how the formula would be reported. And then finally, we would double check that it is neutral. Oh, and it is. Yeah, the plus 2, minus 2, that's neutral. When I look at my final formula, CAS, if I check the charges, plus 2, minus 2, yep, that should be neutral. That adds up to 0. Now, if you had Ca2S2, it still adds up to 0. It's just not the simplest repeating pattern of the crystal. We would reduce the subscripts if possible. Okay, so think about it. Think about what works for you. Here's the 2 options. Let's do the, actually before I do the iron oxide, let's do one like this. Let's look at something like, what if I have, oh, here's a good one. Nickel, 2 chloride. What if they gave me something like this? Nickel 2 chloride. Write the formula for nickel 2 chloride. Well, first, I don't freak out because I see the Roman numeral. The Roman numeral is just telling me the charge on nickel because nickel is a transition metal. It's in that middle D block of the periodic table. It can have lots of different charges. And so, in fact, I don't even have to look up the charge on nickel. It's telling me. The Roman numeral is telling me that the charge on nickel is 2 plus or plus 2. Either is fine. I do have to look up the charge on chlorine. Okay, so I'm going to look up chlorine on my periodic table. There he is. Chlorine or chloride. It's in the group that's always minus 1. Okie doke. So chlorine minus 1. Now, if I think about this by charge, then you just have to make sure that the compound is neutral. And so one way to write these formulas is to focus on the charge and say, okay, the plus 2 means that nickel's going to donate 2 electrons, but minus 1 means chlorine can only take 1. Well, why don't we just take 2 atoms of chlorine? Then each chlorine can take 1 of the electrons coming from nickel. If I want to make this compound neutral, then I'm going to need like 2 times the chlorine. And so you could totally kind of do this mathematically by looking at the charges and saying, what do I have to do to make these add up to 0? I've got a plus 2 and a minus 1. What do I have to multiply the charges by in order to make it add up to 0? So if I have a plus 2 and then 2 of the negative chlorines, that would give me a total charge of minus 2. Plus 2 minus 2 adds up to 0. Done. Neutral. Then when I write the formula, that multiplier, that 2 that I had to multiply chloride by, that becomes my subscript. So I would write it as like nickel, chloride, and then I write a little 2 in there. That this 2, the multiplier, goes down as your subscript. It means the same thing, right? 1 nickel, and then if I had to multiply the charge of chlorine by 2 to make it neutral, then I need 2 atoms of chlorine in my formula. There's one way to do it. And to be honest, that's kind of how I write my formulas. I gotta find the charges, and then I just quick do some very complex mathematics in my head. This is easy, right? What do I have to do to make this add up to 0? Find the charges, and you'll have to multiply. Make it add up to 0. And then anything that you had to multiply by, that becomes your subscript. That indicates how many atoms of that element you need to make it neutral. Now you could also be a crisscross person. If you're a crisscrosser, then you're going to write the symbol nickel and chlorine. You still have to find the charges. You still have to be a freak with charges. But then you can crisscross them. And so you crisscross the numerical charge. Obviously, we don't put like the plus or minus in the final formula. So I also don't have to write a 1. And I would not mark that wrong if you wrote a 1 behind nickel, but we just don't usually put 1s in our formula. And then I could crisscross down the 2. And you get the same formula. But either way, there's no way around step 1, determining the charge on each ion. Once you determine the charge, you can either kind of work it out in your head, like, okay, I just need 2 chlorines to make this add up to 0, plus 2 minus 2. Or you can crisscross them, but don't bring down the plus or minus. In the end, we have to understand the electron transfer, and we have to understand what the charge means. We have to be able to explain the bonding. So I have to be able to explain that the nickel's going to donate 2 electrons, each chlorine is going to take 1. But if you want to be like really fast at writing formulas, maybe the crisscross thing is your mojo. That's fine too. Okay, so then that brings me to maybe like this iron oxide example. Okay, so let's say I'm doing the iron oxide. They're going to give me this. They're going to give me the written name, iron 3 oxide. And so I just have to know then that the Roman numeral 3 means that the charge on iron is plus 3, which is fine. That's cool, right? So it's going to be iron plus 3. And then oxygen, I look it up on my periodic table. It's in the group that's always minus 2. Oxygen minus 2. Minus 2, 2 minus whatever. Here, I'm going to write this, I'm going to scooch it over. So I'm not writing on top of all that. I'll write it over here. The iron's charge is plus 3. The oxygen's charge is minus 2. 2 minus minus 2, same thing. Okay, so you can be a crisscrosser, like they kind of show here. You can crisscross them, just don't bring down the 2 or the 3. Or, bring down the 2 and the 3. Just don't bring down the plus or minus. It's totally fine, it works. Or you can be kind of a charge balancer where you say, how do I make this add up to 0? Well, the common multiple between 2 and 3 is probably a 6, right? So if I take 2 times the plus 3 and 3 times the minus 2, that gives me a plus 6 and a minus 6. And it's neutral, which is what they're showing down here. Oh, then that multiplier boop, 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 just becomes your subscript. Boop, 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 boop. So you'll get the same formula either way. Fe2O3. You can either crisscross the numbers on the charges or be a charge balancer. That's kind of what I am. I'm a charge balancer. I got to look up the charges anyway. So then I just say, well, what do I have to multiply by to get these things to add up to 0? And it's never a bad idea in the end to just double check to make sure that your formula is neutral.